Good morning. Today's topic is piezo resistive transducer. So, we already know that a transducer is a device which converts one form of energy into another form of energy. Particularly, transducers are used to convert non-electrical form of energy into electrical form of energy. Okay. So, coming to piezo resistive transducer means a transducer which converts stress into change in the resistance. Change in the resistance. It is called piezo resistive transducer. So, you know that piezo means stress. Piezo means stress here. Okay. So, if I give stress as an input, then the resistance of the device or instrument will change. So this is called piezo resistive effect. Okay, means if we apply some stress, then the material changes its resistance. This property is called piezo resistive property. A device which possesses this property is called piezo resistive gauges. Piezo resistive gauges. Okay, so we are moving on to piezo resistive gauges, right? Piezo resistive gauges means a device which converts stress, which converts stress into which converts stress into change in the resistance. It is called piezo resistive transducer. Okay. Now coming to the construction or structure. You all know that piezo means stress. Piezo means stress. So if I if I am able to get stress on the material, then the material will strain. Okay. So when a material strains, what will happen? Its dimensions will change. Right. Here, this piezoelectric crystal, this piezoresistive, piezoresistive instrument is a resistive instrument. Okay, the name itself indicates piezoresistive, means if I apply stress, then the resistance of material will change. The stress may be due to force, force. The stress is due to load. The stress is maybe due to load, or the stress is due to torque. It may be due to pressure. It may be due to pressure. Okay, or this may be due to temperature also. This may be due to temperature also. But the strain gauge is an instrument which is mostly used to measure load. To measure load. This strain gauge instrument, the strain gauge instrument embedded with cantilever beam may be used to measure force. To measure force. So, force and load are the very, very much measured parameters by using these strain gauges. Okay. So, temperature, torque, pressure can also be measured by using these piezo resistive gauges. But there are uh, many other instruments for me to measure temperature, torque, and pressures. For example, if we take thermistor is used to measure low temperatures. Thermometer is used to measure low temperatures. Okay. Thermistors are used to measure extremely low temperatures in order of negative temperatures from -60 to +20. Thermometers can be used to measure temperature in the range of 0 to 100 degrees or 200 degrees centigrade. And RTDs are also temperature sensors which are used to measure temperature up to a range of 700 degrees centigrade. Then thermocouples are other instruments which are used to measure uh, temperatures in the order up to 2000 degrees centigrade. There are some other instruments, some other thermocouples like platinum radium thermocouple, which is used to measure extremely high temperatures in the order of 2500 degrees centigrade, 2500 degrees centigrade range. And beyond that range, we have optical pyrometers or simply pyrometers, selective radiation or total radiation pyrometers or optical pyrometers. So these are the instruments which are used to measure this temperature. So apart from these piezo-resistive transducers like strain gauges, there are many more other instruments are available for me to measure temperature. So occasionally I will use this strain gauge to measure temperature. And pressure also, there are many other instruments to measure pressure like diaphragms, capsules, Bourdon tubes, bellows, etc., etc., etc. Diaphragms are also used as a main element in electronic transducers to measure very, very high pressures also. Okay, and I can measure differential pressures also by using this Bourdon tube, by using this diaphragm arrangement of electronic transducers. So there are many other instruments available for me to measure this pressure also. Pressure also. Okay. Examples: diaphragms, bellows, Bourdon tubes, capsules, etc., etc., etc. There are many other instruments to measure pressure also available for me. So these strain gauges are occasionally used to measure this pressure. These are occasionally used to measure pressure. The main importance of these strain gauges are to measure force, load, and torque. Force, load, and torque are the main applications of these strain gauges. Okay, so in industries, we'll use strain gauges much more to measure this load. To measure load. For example, if I want to measure a weight of a coal, I want to measure weight of a coal that is fed to a boiler. That is fed to a boiler. In in boilers, the temperature must be maintained at a rate 925 to 975 degrees centigrade maximum to convert water into steam within a fraction of minutes. Okay, so in order to maintain that much temperature, coal is fed from coal handling plant to inlet of boiler through pocket feeders. Through pocket feeders by conveying coal from coal handling plant to boiler. So this is done by using conveyor belts. So these conveyor belts, what they will do means they will carry coal from coal handling plant after the coal is crushed. After the coal is crushed in coal handling plant, the crushed coal, which is in order of 2 mm to 5 mm, will be dropped onto this conveyor belts, and these conveyor belts will take coal from coal handling plant to boiler. So in this example, I need to measure amount of coal means load of coal, how much load of coal is going into boiler furnace, boiler's furnace. So I will use here the strain gauges to measure load. Okay, means the strain gauges must possess a property such that if the input like temperature, force, load, torque, pressure are applied, then upon depending upon the magnitude of these inputs, resistance of the instrument must change. Here R equal to rho L by A. So so resistance is changed due to change in resistivity of a material or due to change in length of the material or due to change in overlapping area of the material. Sorry, change in cross-section area of material. So I have to choose materials for strain gauges such that if the input like this are applied on it, it must give variations in these dimensions. So let us take a rubber band. Okay, the rubber band has some length and it possesses some diameter also, means cross section area also. If the rubber band is stretched, if the rubber band is stretched, what will happen? Length of rubber band will increase and diameter of the rubber band will decrease. Diameter of rubber band will decrease. Means what? Means what? The dimensions of material are changing. Why they are changing? It has undergone some strain. Okay. Likewise, let us suppose, let us suppose this is this is a material. There is a material having diameter cross means cross sectional area. Cross sectional area as A and length L. Okay. Let us suppose it's a material. Let us suppose L is the length of this material and A is the cross section area. A is the cross section area. We have to choose materials to construct this strain gauge such that if strain is applied, on this strain gauge, then the material should expand or contract depending upon the magnitude of strain. Okay, if I apply strain like this, what will happen? I will take another color to represent strain, to represent the effect of strain. See here, the overlapping area of the uh, cross-sectional area of material will decrease and length of the material will increase. This is the effect. Of course, I didn't draw it in straight line manner, but you think like this. Okay, length పెరుగుతుంది, cross section area తగ్గుతుంది, and it is uniform. Of course, the cross section area of this material must be uniform, of course. So let us suppose delta L is the change in length and this diameter, let us suppose the change in diameter is delta D. Change in diameter is delta D. Delta D is the change in diameter. Therefore, if D is the diameter of the material before applying strain, and upon applying strain, I have delta D change. So now the diameter of this material will be D minus delta D. D minus delta D. And length becomes L plus delta L. Okay. Diameter is decreasing and length is increasing here. Diameter is decreasing and length is increasing here. Right? So the material should possess a property like this. So now what happens? Cross-sectional area is varying and also length is varying, so that R, resistance of material, will vary. Resistance of material will vary. Generally, I use this strain gauges as a bit circuits to measure the input or to measure the input and convert it into a electronics electrical signal, voltage or current. Mostly it's converted into current, not voltage. Okay, so if I apply if I apply force like this, let us suppose I'm clearing my drawing here. Let us suppose let us suppose I'm applying force in this manner. Compressive force I'm applying like this. Let us suppose. So what will happen? Diameter of instrument will of this material will increase and the length will decrease. Diameter will increase, length will decrease. Why? Because I'm applying here compressive force. So even now the length is changing and cross-section area is changing here. Generally, rho is constant for a given material and it depends on temperature and if some impurities are added to it, rho may change for a material. Or if it contaminates, if the material contaminates, then rho will change a lot. So generally rho doesn't change. Material, resistivity of a material doesn't change. It has a value. Okay. So if a metal conductor is stretched or compressed, its resistance changes on account of fact that both length and diameter of conductor changes. Since length, since length and diameter are varying here, since length and diameter are varying here, resistance will change. Also, there is change in value of resistivity of conductor when it is subjected to strain. This property is called piezo resistive effect. Means when a material is subjected to stress, then the material will strain. Due to this, what is happening? Resistance is increasing or decreasing depending upon the magnitude of L and A. So resistance changes. This property is called piezo resistive property. This property is called piezo resistive property. Therefore, resistance strain gauges are also known as piezo resistive gauges. Piezo resistive gauges. Generally, the transducers uses strain gauge to measure load, torque, pressure, temperature, etc. And sometimes it may also be used as a secondary transducer. When a strain gauge is subjected to positive stress, means let us suppose there is a strain gauge material of having length L and cross area A. If I apply positive stress, means positive is like this, okay? Then what will happen? Length will increase and diameter will decrease. Length will increase, diameter will decrease. length increases and diameter means cross section area decreases. Since the resistance is R equal to rho L by A, R equal to rho L by A, since R equal to rho L by A, the resistance of conductor is directly proportional to length and inversely proportional to area. Means if length increases, R increases. If length decreases, R decreases. And if diameter means this cross-sectional area decreases, then resistance increases. If A increases, then R decreases. So this is the relationship between L, A, and also rho also. If rho increase, R increase. If rho decrease, R decrease. So the resistance of conductor is directly proportional to length and resistivity and inversely proportional to its area of cross section. Area of cross section, right? The resistance of gauge increases with positive strain. The change in resistance value of conductor under strain is more than for an increase in resistance due to dimensional changes. Okay, the change in resistance value of conductor under strain is more than for an increase in resistance due to dimensional changes. This property is called piezo resistive effect. So this is the construction of a strain gauge. Okay, these are wires of a strain gauge. These are wires of a strain gauge, right? This is the arrangement of a strain gauge to measure this force. To measure this force. See here, these two are called mounting sapphires. Mounting sapphires. These four are called mounting sapphires. Sometimes they are called sapphire pins. Sometimes they are called sapphire pins. So this is a force rod here. Means if I apply force, then what will happen? Well, what will happen? This this uh, this there now. What is this? This is called mounting sapphire bar. Okay, this is one bar. This is another bar. So since force is applied, what will happen? Then this mounting sapphire bar will tilt like this. It will tilt like this in this direction or in this direction. Okay, it will tilt like this. Okay, it will tilt like this in this direction or in this direction. Due to this tilt, what will happen? If for example, this bar, okay, is tilted like this, is tilted downwards like this. Let us suppose if this bar tilts like this, then what will happen? These two wire lengths, this wire length and this wire length, will decrease, and this wire length will increase. See here, what I will do is I will take a material like copper nickel, chrome nickel, okay, copper nickel alloys. If I take, so these are materials they have used to construct strain gauge. Okay, copper nickel, chrome nickel, and nickel iron alloys are used to construct these strain gauges. Nickel is mostly used. Why? Because uh, it will strain a lot for a given pressure or force, such that its dimensions are changed and resistance will change ultimately. So if I will take these materials to construct this strain gauge. So let us suppose if the time runs out, again rejoin అమ్మా, ఓకేనా? మళ్ళీ మీరు ఒకసారి రీజాయిన్ అవ్వండి. ఒకవేళ కనుక ఇది ఆగిపోతే then again rejoin. So let us suppose there is a wire, nickel wire. This is a nickel wire. There is a nickel wire. There is a nickel wire, or strain gauge wire. There is a another wire. So I am wounding wire like this. Again I will wound like this. Okay. So here the length. See here there is one mounting sapphire here. There is one mounting sapphire here, right? This mounting sapphire. Another mounting sapphire is at this point. Another mounting sapphire is at this point. Another mounting sapphire is at this point. So see one thing, that the material is continuous. ఇక్కడ నుంచి ఇక్కడ దాకా ఉండి మళ్ళీ ఇక్కడ నుంచి ఇక్కడ దాకా కాదండి. మెటీరియల్ మనం చుడుతున్నాం అనమాట, అంతే. అంటే వైర్ మనం చుడుతున్నాము. వీఆర్ వూండింగ్ ద వైర్. There are no cuts in this wire. Okay, this resistance wire. So see here, the length L of this wire is same as length of this wire, and also length of this wire, and also length of this wire. And from this mounting sapphire to this mounting sapphire, length of wire is L. So length of wire from this mounting sapphire to this mounting sapphire, length is L. So length from this mounting sapphire to this mounting sapphire, the length is L of a conductor here. So the length from this mounting sapphire to this mounting sapphire, again length is L. So L is the length here of this conductive wires. Okay. And let us suppose A is the cross-sectional area of wire from this mounting sapphire to this mounting sapphire. Therefore, since I am wounding same wire, I am wounding here same wire. So what will happen? Cross-sectional area is always same throughout the material. Yeah. I am taking the same material throughout the strain gauge. So resistivity rho is also same. Resistivity rho is also same. So rho, L and A are same throughout the material. So resistance here of this wire, let us suppose resistance here of this wire, if I say it as of this wire, if I say it as R1 or R1, resistance of this wire, if I say it as R2, Resistance of this wire, if I say it as R3, resistance of this wire, if I say it as R4, then R1 equal to R2 equal to R3 equal to R4 equal to R, means resistance is same throughout the material. Resistance is same throughout the material. So if I assume this as four wires of a Wheatstone bridge, if I assume this four wires as a four resistors of a Wheatstone bridge, then the bridge is balanced. The bridge is balanced. Okay. Since the bridge is balanced, I'll get 0 as output. I will get 0 as output. I don't get any output. Now I am applying here some force. I am applying here some force. So what will happen? So what will happen? These two wires will get compressed, and these two wires will get compressed, and these two wires will get elongated if this mounting sapphire bar tilt like this, tilt downwards. Then these two wires will compress and these two wires will elongate. So now what is the condition if R1, R2, if R1, R2, R3 and R4 are the resistances here, if I say, then R1, R2 is compressed and R3, R4 is stretched. Since R equal to rho L by A, since R equal to rho L by A, length and cross-sectional area are varying here. Okay, are varying here. So this bridge gets unbalanced. Bridge gets unbalanced. I will get output at the meter. Okay, if I assume this as a Wheatstone bridge. So the current which I get in the meter is a measure of force here. Is a measure of force here. Let us take this example. This is a body. These are the wires of strain gauge. I call this wire R1. I call this wire R2. I call this wire R3. I call this wire R4. If I apply force like this, what will happen? R2, R3 will be stretched. They will elongate. R1, R4 will compress. So the resistance are not same here. Previously R1 equal to R2 equal to R3 equal to R4. The bit is balanced. I will not get any output. But now since R1, R2, R3, R4 are varying here, since applied force, due to applied force, R1, R3 are R1, R4 are compressing and R2, R3 are expanding. Length and area of wires will vary such that bridge gets unbalanced. The output current is a measure of force. Okay. Remaining topics we will discuss in next class tomorrow, not today. Okay. Are there any doubts?
No, sir.
Is it clear for
No,
you?
sir. Yes, sir.
Okay. I'm stopping this recording.